we're going to talk about as well. So without further ado, I would like to call upon our Dean, Dean Gerard D'Souza, to welcome you. He is the Dean and Director of the College of Agriculture, Food and Natural Resources and the Land Grant Programs here at PVAMU University. Dean D'Souza.
Thank you, Dr. Faris. Good morning, everyone.
Good morning.
It's my pleasure to welcome you to the Jill and Mara Daniel Farm and Ranch here on the campus of Prairie View A&M University. We are very pleased to have this great asset, this great resource on which to do research on sorghum, cotton. No, that's corn. But that was a joke. But didn't on the way yet. But I'm very pleased to welcome you to this college. We are a land grant university. We work with our college station colleagues, AgriLife. But at the end of the day, this is what the land grant mission is all about. Bringing communities together with students and researchers to demonstrate some state-of-the-art techniques when it comes to how to manage land for productivity, profitability, but also resilience and sustainability of the land base.
Hey everyone. Good morning, campers and Aggies. Howdy.
Howdy.
Thank you, Dr. Faris, for the opportunity to participate in the Ag Farm Day. I sometimes get confused with the field day, but anyway, it is fun. It's a pleasure to talk about how PVAMU is bringing artificial intelligence and machine learning into agriculture through collaborative, multidisciplinary efforts across our three colleges: College of Agriculture, Food and Natural Resources, College of Engineering, and the College of Arts and Sciences. The Division of Research and Innovation, we call it R&I, supports such efforts through various RISE faculty research development programs and by facilitating research partnerships with industries, R1 universities like A&M, and national labs like Sandia.
Where we have 6 systems. Artificial intelligence is one of them. We have animal systems, plants, food and nutrition, natural resources, this program, and social systems, plant systems, together. Our researchers are pursuing transdisciplinary research. Why is that? Because today's problems are so complex. They need different angles, different disciplines, different experts coming together to solve the problem. Our vision of excellence in research also calls for developing new opportunities. That is, we would like to link the research to success. How do we do it? Our students come and do research. This is a great way of learning by doing. So, we also work with our extension colleagues to extend knowledge, to change the lives, to change the behaviors of our producers. You are all young generation, you solve the problems. One of the best ways to solve problems is to use advanced approaches. So I welcome you again. If you have any questions, you want to get more information.
So the mission of the land grant doesn't finish if we don't have the education, the teaching component. So I'm going to call upon Dr. Aruna Urisuria to also welcome you. He's the department head of the College of Agriculture, Food and Natural Resources. So Dr. Urisuria.
Hello everyone, good morning, and yes, warmly welcome to this program. And you know the artificial intelligence and machine learning is getting more and more popular, and it is going to be in your day-to-day life. So you will see a lot of exciting things what we are doing here, and there are more to come. And we are actually working on the animal side and the plant side also to use the machine learning systems to understand the
Thank you, thank you. I got this area. So we talked about the two legs of the three-partite land grant. So it won't be complete without an extension component. So I welcome Mr. Stedman Douglas. He's our boots in the ground, as they say, right? Boots in the ground, as they say. So he's an extension agent here in the Waller County, and he's going to welcome you as well. Mr. Stedman.
Good morning, everyone. Good morning. Such a beautiful weather, right? Yes. So I just want to welcome you all, especially first I'm going to start out with my farmers who are the bedrock of this community, of this nation.
So he became a very, very Aggie, as if he was trained in Ag school. So welcome, Dr. Awal.
I printed this few pages. Maybe you have this one or this one. But this is about this field experiment. Like here we have 3 field experiments in this small area. So if you see here, like this one is 3 rows. We use different organic amendments, chicken manure, dairy manure, and biochar. And also we use different amount of chicken manure, different amount of biochar, and different amount of dairy manure. These 3. So these are like in our row, like we have 14 different treatments. Then all of this is and this is out of the then those are 4 rows. Like those 4 rows, like different, you can see we use different amount of irrigation. Like first row without irrigation, and then second row we apply this amount of water, and then third row like we apply how much water plant needs. This we apply, and then last one like we apply more water. So the main objective of this experiment, like based on those different types of organic amendments, based on different amount of organic amendments, how they will impact the plant growth, soil properties, and then greenhouse gas emissions. Those we are trying to see in this plot. And like we are using different amount of water. So like based on amount of water we apply, how the plant water space will be different, and then how the moisture content in the soil will impact the plant growth. We are also checking it out. So in that experiment, not only different amount of irrigation, like we are also using different amount of biochar. So in each row, like we use 4 different types of biochar, 4 different amounts of biochar, like 0, 5 tons, 10 tons, and 15 tons per hectare. And then, so in each row, like 3 replications. So 3 times 4, like we have 12 pots in each row. All those 4 rows. We our digital twin, like digital twin, like our plan is to grow crop digitally, not only in the field, also based on different input data. How can we grow crop digitally? So in this particular plot, like we install some additional sensors. So like this one has like soil canopy, soil moisture, soil temperature, plant canopy temperature, NDVI. Those data we can access online. So all those data directly connected to online. And we have these 2 weather stations, and one of these weather stations that one is also linked online, so we can access data from this part of the weather station directly online. Like API, we can get the data. And originally, like we tried to use this block for like real-time input data, and then grow some crop digitally near real time. But there is some other difficulties, like this field we don't have Wi-Fi connection, and then we could developing like 3D image of this plant. We couldn't do that. But we are collecting data, and that data we will use for developing that digital twin model. Not only this plot, like we will use all those information from different plots we will use for that model development. So this part, like this one is collaboration with Texas A&M. Dr. Jen Tao, he's here. He's exploring digital twins. So if you have any questions related to digital twin modeling, he can answer.
You wanna give a little bit more information about the project?
So we are taking the data from the sensors and try to build a machine learning model. And currently, I have students here to build the visualization for the field. So we have a video created at the very beginning of the project, just to showcase how this the crop. Back then we started with the sorghum, but now we switch to corn. We are trying to simulate how the plant grows visually. It's kind of like animation you're creating, but it's controlled by parameters. So the parameters could be controlled by the sensors we're getting. So based on the irrigation and also the measurements from other sensors, we can change the way how the plant grows visually. And the long-term plan is to build the machine learning models based on the sensor data and visually predict the different scenarios. Given different irrigation models, different sensor data, how can we visualize that whole thing? But in the longer term, we want to create a system that can not only show you something, but also give you some predictions about what could be done to increase the efficiency of the crop, or increase the water usage efficiency, or other things. So that's some work that Dr. Arwal is working on, but we are mostly helping building this system to get everything connected using the sensor network, using the different networking technologies. Thank you.
You may want to ask, I think to add a little bit clarification about the digital twin. You say, why are we taking this, doing this experiment? So originally, before we used to simulate, we have software to simulate the crop growth and predict yield and predict the diseases, etc.
Thank you, Dr. Paul. Thank you everyone for coming. We are measuring the soil greenhouse gas emissions, which are mostly three gases we are measuring. Those are carbon dioxide emission, and methane emission, and the nitrogen dioxide. So we have two experiments over here, as you also saw that we have two experiments set up. One based on the amendments, different kinds of amendments we have put here, and we would like to see what are the emissions from different applying different amendments for dairy manure, for chicken manure, for biochar, and for the controls. What are the difference between the greenhouse gas emissions over here? And as well as on the left side, that experiment we have applied different amount of water as irrigation water, and we also want to measure the greenhouse gas emission from that. So we are measuring the greenhouse gas emission with the Lycor 7810 model trace gas analyzer. As you can see here, we have two analyzers. One can measure the carbon dioxide and methane, and the other can measure the nitrogen dioxide. And the process it actually measures the concentration of the gases. This is a box, the chamber. This chamber, as you can see, there are a number of collars in every plot. So we put this chamber on the collar, and then it creates a vacuum that can trap all the gases inside this. So So it, yeah. So putting this, if we have the
soil, the more accurate the temperature is. And once I do that, I write the data down, and then I go ahead and take the leaf temperature. So initially, we started taking the temperature of the 5th leaf, but since each crop starts maturing, we start taking temperatures for the 9th leaf. And for each plot, I realized that prior persons, when they're talking about the experiments that we have 2 experiments here. So the first experiment, there's 3 plots. So each plot, each row has 13 plots. Well, excluding this one because it's has an extra plot. And then the other experiment is the last 4, and that has 4 rows, and each row has 12 plots. So the first experiment is called
Climate smart.
Climate smart. And the last 4 is AI in agriculture. So that's the difference of the experiment. So each day when I come, I'll start with the first experiment, take the measurement, and I have to ensure that each time I take the measurement, I write it down because it can disappear. And then the next day I'll just continue and do it, and throughout the week I just do it simultaneously. So it's a little easy taking the temperature down, but it can be hectic because it includes a lot of bending and stooping, and then it's the sun, it's really hot outdoors. So it isn't much to do, so yeah, that's about it.
Go ahead, Kinza, and add more information about what you do.
Yeah, of course. So Akelia and I basically almost do the same thing. We work on every plot. She takes measurements from 4 plants in each plot, and I use these thermometers, which I put into the ground, and I choose the same location on every plot. So I will go to so I do 3 measurements. So I will go to the 4th plant, and then the 7th plant on each, and then I will stick this ray all the way into the ground and just wait for the measurement. And like Akelia said, it's not a lot, but in the heat and stuff, it takes a while. But yeah, so the reason we get soil temperature is we want to see we get a lot of rain and stuff. We want to see how the soil temperature is changing, not only with the weather, but we have different levels of irrigation on each plot. Like for example.
Hello everyone, good to see you out this morning. So this is the cone penetrometer. So it does have a cone tip based upon the pressure of this soil against this tip, but it's held vertical. That, and then as you move it downward, you're going to get more pressure because the soil has more structure. And you get a digital reading on this unit. There's a set of these that are actually set up with GPS, global positioning systems, such that wherever you're located, when you take the reading, that you also have your location. You can actually map out the whole area that you're focused on. At that point, you can do a map, and it can actually tell you where the soil is most dense. So at 300 pounds per square inch, that is 300 pounds of force exerted on this one point. That is the point at which roots will not penetrate the soil. So when you know that, you know that the soil is not going to get any nutrients from that area below because the roots can't penetrate there. So this is the importance of using the cone penetrometer for soil compaction.
Thank you, Professor Griffin. If you have any question about soil, you want to understand soil, you have an expert here. Professor Griffin is great at explaining things related to soil science and what matters for our crop, etc. So next we're going to talk about, and Dr. Owl mentioned about these, the PSR Plus, which measure the spectrum of light, because that's the reflection of that light through the soil or the plant can tell you can see the health of the plant. You can see if the plant has nutrients or not, if deficient or not, if diseases, etc. So we do have 2 other instruments that Kari and Professor Vito is going to talk to you about. That we call them NDVI and what's the other one? And SPED meter, right? Please go ahead. Dr. Vito, he's a Barry is a graduate student at the College of Engineering. He's working with Professor Awad with us. He's a very reliable person. Get go, you will take care of it. It's in the field. Assume it's done.
I thank you very much. My name is Akari. I'm an international student. Part of this great project, and I'll be explaining to you how this expand here is actually come out of soil plant analysis. We use it to measure chlorophyll levels, actually to check for nitrogen deficiency. So in the field, what we do here is we measure tree plants. We take tree plants on fall. We measure the tip and the bottom of the leaves. And then we average that data. We record. That's
Our project called Get Act Smart, which is about teaching young generation, empowering them with new technology, the AI, robots, and the good stuff. He's going to give us some highlights about that project. Okay.
Thank you so much. I promise I'll be brief, but I will begin by saying it's such an honor to be here. Thanks for inviting me out. Every time I come to this campus, I'm always impressed with just what's going on and how you all are pushing, as we would say, pushing the needle, and seeking excellence in what we do. Always been and very impressed by your review. So again, thank you for having me out there. You know, my students would say affirmation is not my thing. So when I thank you for your excellence or seeking that, it's very authentic for me. So to really be brief about the Get Ag Smart project funded by NEFA, what Dr. Fairs and a couple other faculty members have done is create an educational intervention in undergraduate courses, both at Prairie View and at Texas A&M University. And so what that data is found of over 900 respondents, and I'm a social and behavioral science. What I study is what's being taught here, if and how farmers are using it. That's what I study, and the impact.
Mr. Ahmed, please go ahead.
All right, thank you, Dr. Faris. Hello, everyone. My name is Ahmed Abdul Ahmed. I'm associate professor in the Department of Computer Science, College of Engineering. I'm here today to present our IoT experiment, Smart Irrigation Ag here. So my grad student is going to show a demonstration on how we can sense the soil moisture on the soil here, and how we can use a mobile app and smart technologies to turn on and turn off the pipe based on the moisture on the soil. Go ahead, please.
So it's a smart IoT project. It's called, yeah. So it's a smart IoT project. It's called plant watering system. So as you can see, I have a soil moisture sensor here. So it automatically monitors the moisture, and this is ESK8266. It's a node MCU, and we have LCD monitor here. So whenever
normal wheel design, there's enough friction or there's enough resistance, the wheels open up depending on how many or how the soil is reacting. So if we have an obstacle that we need to traverse, the wheels open up passively without me doing anything. So just like operating it normally. And for the data, we can collect it, save it on the robot, but we can also view everything real time. So I'm viewing the camera information right now. Yes.
Thank.
In the same way how we can see the camera view here, we have collected some of the data on that particular robot that is related to just one particular crop row, so that can be used offline for further training purposes, where it can like navigate just based on the crop row width, detect if it has like good corns and if the corns are ready to be harvested, or if there's any pest on any of the leaves. It can like autonomously detect if there are any pests that needs to be further treated, and then let the user or anybody who's managing the farm know that, okay, this is the issue which needs to be cured for a good harvest.
Thank you, Neha. Thank you. Any questions that you have?
This was mostly built with the ability to navigate on rough terrains and with a special focus on stairs. This can climb over stairs as well. all these robots are built to be used on the field for agricultural data collection purposes, so that even if the terrain isn't that great, this particular wheel mechanism can like navigate on the terrain, make sure the data collection is accurate. Along the same side, we have another robot. This is based from Iron Robotics, the chassis, but all the sensors and components have been inbuilt and made sure like everything works pretty well by some of our old graduate students. And this can be used pretty well for like any kind of like data collection. Like these can like navigate through the crop rows and collect any data that can be used for training a custom machine learning model that can be used again towards autonomous navigation in the field or for detecting yields for any of those particular purposes. So these two robots are controlled autonomously, as well as we have a PS5 controller that can be used to control the direction of the robots. Like right now this is turning, and then if you want it to go forward, it can go forward as well. And these two are connected to a mesh network that we have installed in here, so that even if we have like multiple robots on the field which are again connected to the same mesh network, they can like collaborate together and then work. Can I give a demonstration?
Of course.
And we do have another...
What do you want me to help you with? Okay.
We do have another mechanism for the same wheel-like mechanism, wherein the wheels can like rotate and move if it has to like walk. This is called like a wheeler-based mechanism called Alpha Volta, so that it can just walk based on any obstacle that it has detected. These wheels are passive mechanism and they do not have any active actuation component installed on it. Like, this is just like a gear mechanism where it can close and open. Quickly make sure the robot navigates to one of the consoles for the data collection.
Can we ride on it? So anyway, while we're waiting for the robot to come back, we have another Professor Siva. He's also a collaborator with us, and so his students came and show us the drones that they are using. So we're working on a joint proposal to develop some proposals for funding.
Answer problems, and you can spray them selectively, and you don't actually have to go out.
Ready, one. He said, hello, one.
PV, you know.
Hello, hello. Stay where you at. All right, 1, 2, 3. One more, 1, 2, 3. All right.
Pastor Wall, he wasn't to the picture. Can you please?
Okay, no problem. Got it.
Thank you.
Thank you, sir.
Thank you, AD.
How can we contact you for the photos?